I'm going to be talking today about petabyte scale data analysis with Apache Pinot here at Stripe. Um, our agenda today is I want to give you an overview of what real-time analytics looks like at Stripe, and then I'll be digging into a specific case study around how we track financial events. I'll be talking about how we model the data, how we leverage Pinot to serve queries, and some of our performance results and next steps. So let's first talk about Stripe. You may be familiar with Stripe. We offer online payments for a variety of businesses. What you may not know is that Stripe is vastly complicated, and we offer many products. We offer payments, we offer loans, bank accounts. You can create your own credit cards. You can accept in-person payments, etc. So lots of complexity in our product layer. We also have a growing geographical reach at Stripe. So many of these countries, or many of these products are available in 43 countries, and we support 143 different currencies. And finally, Stripe's scale is pretty massive. To give you a sense of this, we've received 173 billion API requests just in the last 12 months, and this is growing rapidly. So let's talk about some of the use cases for real-time analytics at Stripe. This is somewhat focused on the financial data space. This is the organization that I'm in. But I want to highlight some of these areas. So we use real-time analytics for generating financial statements and reporting. So think income statement, balance sheet, detecting bugs and problems. So when something breaks, we need to know about it very, very rapidly. Detecting financial risks. So problems that may crop up, maybe a risk of loss in certain cases. We need to identify and flag those early. We need to manage Stripe's liquidity across corporate entities, across many countries. And finally, we need to audit past actions. So we need a rigorous log of things that we've done to prove what we did and why and have evidence for it. So this is true of many organizations, but I want to highlight a few specific problems that we see in the fintech space. I think Stripe is a great example of these. So first, with real-time analytics in the fintech space, we have very, very high precision accuracy requirements. So our aggregations must be exact. Floating point numbers often are not precise enough for these purposes. So even doubles, we see variances. And decimal points vary a lot by currencies. So not every currency treats decimal places the same way. And we have many cases where we have very, very small amounts of a currency, think, fractions of a penny that we need to track and understand rigorously. We also need to keep transaction level granularity. So what this means is that aggregates are often required for reporting. However, we need the original transaction level data, and this is related to audit and debugging and investigation. Reports must be reproducible. So any report that we've produced in the past, we need to be able to understand the data that went into it. If it changes, we need to know why. If you send a report to a regulator and they ask questions about it, you need to be able to answer those questions and prove what you produced there. We see frequent manual action to remediate problems in the data, more than you might think, given a very automated fintech company. And so for this, we need observability, and we need to be able to quickly update and see the results of our updates. And finally, I've alluded to this several times already, but we have very strict compliance and security requirements. So we have very sensitive requirements about who can see what data, where customer data is visible, where bank account data is visible, et cetera. So we need control and governance over all of our data sets. So that was a high-level overview of how we think about the real-time analytics space. The next section, I want to dive into a specific use case at Stripe, which I'll call tracking financial events at Stripe, and I'll explain what that means. So what problem are we solving? So as you might have guessed, there are literally dozens of engineering teams at Stripe that on their own move money around. So different products, different countries, different currencies, different banking integrations, et cetera. There's a huge amount of complexity here. And all of these teams are often using different platforms, sometimes different programming languages, yet they're all creating events that have financial impact. And we need to understand those events downstream. So accounting needs to know about these events to produce financials. The finance team needs to know about these events to forecast the future, to understand the company at the present. Data science needs to understand these events, etc. So we have a clear need for mediating many teams on one side, uh, creating financial impact, and many teams on the other side who need to consume and understand that. But there's another problem here, which is that in that data pipeline, we also need to observe and take frequent action when things don't look correct. So data quality is very, very important with our financial data. But also we need to, as I mentioned, spot problems and spot risks, understand when something breaks, especially when it has financial impact, and we need to take action on that. So how do we accomplish these goals? Well, the solution at Stripe is a system that we call Ledger that sits in the middle here. And what is Ledger? So Ledger is a batch financial data processing system, and I'll tell you a little bit about how we've designed it and some of the key characteristics. Ledger has a unified data format for all of its events, meaning regardless of what team they come from, each event has the same common schema, and thus the downstream consumers can rely on that schema. The schema is slightly interesting. It's a double entry schema, meaning that for every event, we are logging an A and a B, meaning we're saying there's impact to A and there's impact to B. And I'll talk more about this in a second. The events are stored in an immutable log, meaning events are never deleted. So this is critical for our reproducibility and audit requirements. We need to know that any query we've run in the past can be reproduced faithfully in the future. Every team that moves money then must integrate with this system. And so we have a client-side library that they use. We call it a bookkeeper, and they use this to log events into the system. And just a brief description of the architecture, we receive events over Kafka from upstream teams, and we process these events in Spark. So I alluded briefly to the data model here. We use a double entry data model, and I want to explain more about what that model is and why we use it and some of the useful characteristics that it gives us. I think this is quite interesting. So first, I want to underline that when Stripe undertakes an action, for example, processing a charge or paying out money to a merchant, there are often many steps within Stripe that are necessary to take that action. So if you think about what it takes for Stripe to pay money that Stripe is holding out to a merchant's bank account, it's actually pretty complicated. So we need to take the money out of the merchant's balance. We need to create a payout. We need to batch these payouts together. We need to submit these payouts to a bank. We need to then receive reporting and confirmation back from the bank. And then finally, we need to reconcile the bank reporting back to the original payout that we wanted to create. So remember, these are financial events. So every step here has financial impact for Stripe. And if anything here breaks, we need to know about it immediately. We need to action it. We need to fix it, etc. We also need to know the state of these funds at the end of the month for our financial reports. So if a payout has been taken out of the merchant's balance but hasn't yet been sent to the merchant, we need to record that too. We can't just drop money out of our financial statements. So the ledger data model is how we wrangle this complexity effectively. And here's how it works. So let's say you have an event and you want to record, basically we're taking an action with money, we're moving it from A to B. So the way we model this is we'll have something called an account A and an account B, and these will be specific to this transaction. So a single charge is a single account. And the event will say, okay, we're moving $10 from A to B. This is useful because we record an event, we record metadata on the event, we record an action that's been taken. Um, but then it's also useful because we can string these events together. So another event can come along and say, okay, we're now moving money from B to C. So we've moved $10 from A to B to C. And this isn't quite a state machine, but you can model it very close to a classic state machine. In other words, you can then track money moving through the system, moving across teams, waiting for reconciliation. Um, and the way that uh, a critical piece of this is that we have a balance associated with each account. So, in other words, the impact of these events creates a balance in each account A, B, C. So here, the B account has a $0 balance. So this is key. This is key. The reason this is useful is what if event two doesn't work correctly? What if something goes wrong? In this example, we're saying money moving from B to C was only $5. And so we retain a balance of $5 in account B. So the way we've designed the system is that most of our accounts will clear to zero. Um, and if it doesn't, that's a very, very strong, good indicator that something is broken. The reason it's good is it's generic to each account, number one. And number two, it's very hard to break this mechanism. So what if we accidentally pay out to a merchant twice, or we pay out in the wrong amount, or it doesn't happen at all? You would still end up with a balance in account B. So this is a powerful observability mechanism. So to summarize our data modeling here, we record events as double entry events that impact at least two accounts. The entries to these accounts must net to $0. The accounts are transactional, so one charge is one account. And most accounts should have a $0 balance. So here what you can see we're setting up is we're going to have certain query needs over these data models. And so I want to talk more about this in the next section. So how do we leverage Pinot to track and serve this data model? Well, we have several query patterns that we need to answer, given the model I've just described. So first, you need to be able to look up a specific event. Often these are tied to IDs that are inside Stripe. So an account ID, a charge ID, a payout ID. We need to be able to look up and inspect events. Next, we need to be able to look up and inspect accounts and summarize them. And so remember, there could be many events tied to a specific account. And so we need to be able to query an account and then grab a list of all those and aggregate into a balance. Next, we may need to aggregate many accounts. So we may ask a question like, for all payouts, are any broken? And in this case, we have an aggregation over potentially millions or billions of accounts, and we need to query them all and aggregate balances. So this is a pretty easy problem until you consider Stripe's scale. So this data set ends up with literally hundreds of billions of rows, accounts in the millions in many states of transitions. It needs to be very fast and fresh and up to date. And we need to be able to serve to internal customers with sub-second latency. So we need an interactive UI, think slice and dice view over this data. So these reasons are why we decided to leverage Pinot. We have a hugely large data set. We need to scale it. We have several different query patterns that we need to serve with low latency, and we need to keep our data quite fresh. So we've researched and we decided on Pinot as the right system to answer these problems. And I'll give you an overview of the architecture we've ended up with here. So uh, we have a fairly large Pinot cluster in the 1,000 plus node range. We index the cluster batch and streaming. So we load this cluster frequently from Spark, sometimes for backfills. Uh, and then we also have streaming ingestion. So we also pull directly from a Kafka topic and inject this data into Pinot. So two write pathways. And then on the read side, we use Pinot to power internal UIs, some internal checks, and analytical queries. So high-level overview of our architecture. I want to talk a little bit more about the data scale that we operate Pinot with. So given Stripe's financial complexity and given the number of actions that we take, our data set ends up in the hundreds of billions of rows, and this is currently for us roughly around 700 terabytes of storage on disk after replication. And so this is one of the, if not the biggest production Pinot table, or so we're told. And spinning this up and making it work well required tuning and experimentation, especially with indexes, with node sizes, memory and disk allocations, etc. So where we've ended up currently is that we run about 1,000 plus node cluster on Amazon EC2. That's around 4,000 CPUs with attached SSD for this cluster. We selected this configuration based on experimentation, on performance and cost. There's always a performance cost trade-off here. And in terms of Pinot configuration, we have two sections. So we have offline segments. These are the segments that we batch load. So we have about 60,000 segments per table here. And we have a real-time table that we can query concurrently. And this we've divided into 64 partitions. And I believe this matches the number of Kafka partitions we have. I want to talk a little bit more also about how we achieve the financial precision and accuracy results that we need with Pinot. I think I call this out because I think it's a somewhat unique to fintech problem, and I think it's interesting how Pinot has managed to solve it. So, as I mentioned, we execute aggregations over many accounts at one time, and often what we're looking for is a reading on whether we're aggregating to $0. So does the sum of all of our credits and all of our debits sum to $0? And so accuracy is quite important in these cases. And Pinot is useful because it gives you some control over how accurate you want your aggregations to be. And so we've tuned basically to as accurate as we can make it, and seen only really minimal performance penalty. We also treat deduplication as quite important. And so something that I wanted to call out here is we also leverage Apache Flink upstream of our Pinot cluster. And this is responsible for deduplication, duplicates coming from the Kafka layer or from the application layer in some cases. And then we're also leveraging the Pinot upsert in certain cases. So we're using both at different times. We also care a great deal about financial precision. So as I mentioned, floating point math is generally not precise enough for financial calculations. And so we use big decimal in our own code extensively. And this is now also a feature in Pinot. And so I wanted to call this out as something that we care greatly about and found a very useful feature set in Pinot. So Pinot supports big decimal for binary columns. And these work really well for us. So We're able to execute the sums, the aggregations that we need. We can apply star tree indexes, and we haven't observed a significant performance penalty. So ultimately, the precision has worked quite well for us with Pinot. So what does performance look like? So these are fairly high level results, but on average, we're seeing for single transaction lookups. So these are basically point lookups for to power internal UIs. We see median query times of about 50 milliseconds and 95th percentile query times of around 200 milliseconds. And then for rollups, which is an aggregation query pattern, we see median around 100 milliseconds and P95 around 300 milliseconds. So we think these are pretty impressive results given the size and scale of the data here. Again, we're talking about 700 terabyte data set here that is constantly being updated with new information from Kafka and batch loaded in certain cases. And we're able to rely on Pinot to serve queries in times that are fast enough for internal customers. So think of an ops person experimenting with the UI, slicing and dicing the data, looking at different views to get more information. So Pinot is supporting this case really well. So what's next for Pinot at Stripe? So we're going to be onboarding additional internal tools to Pinot. It's proved quite useful for some of our internal ledger search capabilities. But we also have many other critical tools that we also have similar needs for. So maybe a large data set, maybe we need more flexible queries, et cetera. We're also going to need to scale with Stripe's growth. Stripe continues to grow very rapidly, and so we expect that our data set next year will be significantly larger than it is even today. We'll also be using a very cool Pinot feature. It's called the Presto connector, which plays very well with some of our internal capabilities at Stripe. So we're big Presto users, and the ability to query Pinot from Presto, join disparate data sets works really well for us because we have a ton of dimensional fact tables in Presto, and we want to, in some cases, combine, join them, et cetera, with Pinot tables. So we'll be leveraging this more and more as we go forward, I expect. And finally, I expect there'll be many other applications of Pinot and Stripe. I've already heard interest from a handful of teams, and given Pinot's capabilities, I think it'll be widely used in the future. So that's all I have today. I hope this was an interesting presentation and a unique dive into some aspects of problems that we see as financial infrastructure in accessing, using analytics, and gives you a sense of how we're leveraging Pinot to solve some of those problems.